The angular speed omega of a point moving in a circle is defined as the quotient theta over t, where theta is the angle in radians through which the point travels in time t. A. Find the angular speed of a point that moves through an angle of 4 radians in 6 seconds. Alright, so let's determine what part A is. So, we're trying to find the angular speed. Notice this is already angular speed, but we just have to reduce this. Right, so we're going to take 4 radians for 6 seconds and reduce this by dividing both of these by 2. Alright, it's as simple as that. So it's going to be 2/3 radians per second. Right, simple as that. Part B. Find the angular speed of a point on the rim of a wheel that travels 60 RPM, revolutions per minute. Okay, so RPM stands for revolutions per minute. So we're talking about 60 revolutions per minute. So we're going to notice where we need to convert. We need to convert to radians per minute. Okay, radians per minute. Right now it's revolutions per minute. So we're going to take 60 revolutions per 1 minute. We just have to convert the revolutions to radians. Right, so we know 1 revolution is 1 full circle. Alright, so that means we can convert the revolutions to radians by noting that 2 pi radians take exactly 1 revolution. Right, so 2 pi radians take 1 full circle, and we know 1 revolution is 1 full circle. Right, so as a result, the revolutions cancel out, and all you're going to have is just 120 pi radians per minute. Notice that we're doing per minute because this is already a really high number. We don't need to convert it to seconds. Right, so part C. Part C is a proof question. It's basically a theoretical question. It says, show that the linear speed v of a point moving in a circle is related to the angular speed by the formula v is equal to r times omega. Right, so first what we're going to do, we're going to recall that we can express s equal to r times theta. All right, now know what does the s stand for? S stands for arc length spanned by central angle theta. Right, so basically when we have a circle, and let's say we have a central angle here, theta, we know the arc length spanned by this theta is going to be this arc here. Okay, so notice that this is going to be the s. Right, that's going to be the length of this arc. So s, to find that length, is going to be multiplying the radius. This is the radius times that arc spanned by the angle, central angle theta. Right, so if we're going to do that, we're going to find, we're going to make it actually interesting. Notice that the linear speed is found by dividing this s by t. Right, because the speed along the edge of the circle, all the way around the circle here, is going to be the linear speed. So we have to divide both sides by t in order to solve for the linear speed. So what I mean is that if I divide s by t, I have to do the same thing on the right side. So it's going to be r theta divided by t. All right, and notice what that is going to give us is precisely r omega. It was given to us before that the omega is equal to theta divided by t. All right, it was given in the first sentence. So that means if I multiply both sides by the radius r, I'm precisely getting this, r theta divided by t, which means that the omega must be also multiplied by the radius, right? So that means the linear speed is equal to the radius multiplied by the angular speed, omega. Okay. So now that we have that, what is that going to help us? So s divided by t is the arc length speed, linear speed, right? And now let's get to v. So v is going to be what? V is shown to be the linear speed. So v itself is s over t, right? Because we determined that s over t is the arc length speed, the linear speed, right? So v is a substitution for it. All right, so that should be equal to arc theta divided by t, right? Because we determined that the linear speed is equal to the arc theta divided by t. Thus, and we know that arc theta divided by t is r omega. So that means by substitution, v is equal to r omega, the end result. So we've successfully showed that indeed this equation is true. Right, so the last part now is again the mathematical one, not the theoretical one. It says a car is moving at the rate of 60 miles per hour and the diameter of each wheel is 2.5 feet. Find the angular speed of the wheels, right? So remember I said that imagine the circle is the wheel of a car. So this is an example showing that. So we have 60 miles per hour. Notice that this is the linear speed, right? Because we're talking about the car moving at that rate. It's the speed of rotation along the edge of this circle. Okay, so now, and the diameter of each wheel is 2.5 feet. All right, so we need to convert that to angular speed. So linear speed conversion to angular speed. So again, we use v is equal to s divided by t. All right, and we're also going to say that s divided by t is the arc theta divided by t. We're going to use that. It's going to be very important. Then notice that we can solve for the angular speed. Remember that the angular speed is defined here, theta over t, right? So theta over t is the angular speed. And notice to solve for the theta divided by t, we just divide both sides by the radius, right, to get rid of it. We divide both sides by the radius, which means that the radius here will multiply the t on the bottom, right? So it's going to be s divided by rt, right? So that's going to be very important, all right? So let's circle that. The angular speed is going to be the linear speed divided by the radius, all right? That's basically what you see here. Okay. So also notice that r is equal to half the diameter, right? Because the radius is always half the diameter. The diameter is 2.5. So we have to divide 2.5 by 2, which is 1.25 feet. So we're going to use that as well. Okay, now let's proceed with the conversions. So we're going to first find the linear speed. So s divided by t is what? Is 60 miles per hour. But this is not linear speed in terms of what we want, because we want to convert it to feet per minute. And why? Because you see the diameter is given in feet, right? So we have to convert miles per hour in feet per minute, right? So we're going to take what? We're going to take 60 miles per hour, and then we're going to multiply it by the conversion factor that 1 hour takes 60 minutes. That's good. So the hours cancel out. And then we have to also multiply what? The conversion factor that does the miles versus feet. Right, so we know that we take 5,280 feet per 1 mile, right? And that successfully cancels out the miles. All right, so if you do this carefully, 60 over 60 is just 1, so you're left with 5,280 feet per minute. 5,280 feet per minute. So what you just found is the linear speed of the wheels, right? It was already given in miles per hour, but you just converted it to feet per minute. Right, so now we can proceed with finding the angular speed using this equation here that we've derived. So then, theta divided by t is going to be what? Notice that we already found the s over t, which is 5,280. Remember that we said we have to divide the linear speed by the radius. Okay, so that means we're going to take 5,280. Okay, and you're going to divide it, notice that we're talking about feet here, and you're going to divide it by 1.25 feet. So this is per minute. And you're going to divide it by the 1.25 feet, and notice that the feet cancel out, and this conversion factor automatically has the radians per minute. All right, you don't see radians here, but since we're talking about the angular speed, we're talking about the radians per minute. So notice what this is going to give it to us is 4,224 radians per minute. Thank you so much for watching. I hope this was helpful. See you in my next videos.